In our last class, if you remember, I have already explained the definition of cryptography and then few terms like plain text, ciphertext, then encryption, then decryption, cryptography, cryptanalysis, adversary, cryptology, symmetric key, and asymmetric key. So the last examples that I already given to you was the examples of few examples on symmetric key cryptography. That means both the senders as well as the receivers they share the common key. So that was the key. Both the senders and the receivers they share the common key. So for example, is Scytale Cipher. So it was used by Spartans around 50th century. Is that cipher clear to all of you? So I explained in my last class. Okay, I asked you how to do attacks. Any guess that you can find this? How to attack this? Okay, maybe after in the exam question I may put like this. Okay, then another was
For the Spartan Scytale Cipher,
yeah,
to decipher it, we must know that how many alphabets can be accommodated in a single row.
yes, good.
So if we can know that how many alphabets are there, then every if there are k alphabets in a single row, then the every kth alphabet for comes in a single phrase.
Yes.
And in
So
this
that
way,
means when you are an attacker, you don't have that idea how many alphabets you can accommodate in a single row. So you have to guess. That means so there is a kind of periodic things, right? So you
yes,
have to guess the period.
yes, yes,
That means if you write it in a row wise in a matrix form, then when after exhausting the first row, it will come to the second row. That means from first to second, the number of columns is basically the period. So you have to guess the period. So you will have some long string of alphabets. Say first you guess, okay, maybe 10 could be the period. Then just try to place the first alphabet and the 11th alphabet and the 21st alphabet side by side and check whether you can have some meaningful words or something. If you don't find it, then say start with the period with 11, then first and 12th and 22nd could be the consecutive alphabets that we put side by side and try to find whether any meaningful things you can come up. And in that way, by using computers, it's very easy to attack this kind of schemes. So they are known as attacks. So using computers, you can very easily model this kind of attacks. So then I gave some example of Caesarean cipher, and it was explained in my last class. And we have also seen how group theory plays an important role in giving the in understanding this ciphers. But surely Julius Caesar had no clue about the formal definition of group theory because group theory came much later. Okay, so Julius Caesar did it in a different way, but now with the help of group theory, you can explain it, the encryption and decryption function very easily. And we have also checked how to give a attack on that, and you have seen that within 25 or 26 tries, you can always break the scheme. So one of the basic problem you may find that this is due to the there are only 26 many options. That is the size of the key space was too small, only 26. That is why the cipher could be broken very easily. Now we again went for another little generalization of the SIP cipher that is known as affine cipher. And in the last class, we have already seen the encryption function of affine cipher, and we have also showed that this is a generalization of SIP cipher, because if you put a equal to 1 here, then this is nothing but the SIP cipher like the Julius Caesar cipher. So this scheme could be thought of as a generalization of chip cipher, and we have already seen the size of the key space was 26 into phi of 26. That means 26 into 12. So it's a little more than what the key space was for Caesarean cipher. So in that way, this scheme could be considered as better scheme than SIP cipher. Then we talked about a little bit about Ruby cubes, and then we came up with the substitution cipher. In substitution cipher, so this every key is nothing but a permutation. Since there are 26 factorial many permutations, so you can understand that to break the scheme, one has to understand or one has to do 26 factorial many options for exhaustive search. But later on, I have shown you that there is a concept called frequency analysis, which is a statistical test or statistical analysis, which actually gives an efficient attack on the substitution cipher. And if you write it the programming in an efficient way and you associate your algorithm with library functions of dictionary, so if you add the dictionary with your program, then within half an hour or 45 minutes, you can break the system, half done by using the machines, and then by visually you can break the scheme very easily. So that means though the size of the key space was 26 factorial, a huge number, more than 4 into 2 to the power 26, so it's a huge number, but still you can break this in an indirect way by using some statistical analysis within maybe half an hour or 45 minutes. So that's very efficient way of breaking the scheme. So that's why what I tried to mention you, it's like it's not that if your scheme looks very complicated or if your scheme has large key space size, it does not mean that your scheme is very secure. So security comes from a different viewpoint, and many people are trying to break it, and if somebody will get some tricks to break it, then the scheme could be broken. So that's the basic idea for attackers or hackers. They always try to find some loopholes or the usual mistakes that the users usually commit. So depending on that, they uh, give a kind of attack on every schemes. Okay, now let us have a look at these schemes where if you in case of say Caesarean cipher also, if you see that in case of Caesarean cipher, if any of your alphabets, for example, say using K, if you have C, that will always go to N, right? So that means in the cipher text, wherever you will find N, and if you have used k equal to 11, then you know that where the plain text will always be C. That means C will always go to N, R will always go to C, Y will always go to J. That means if you are using k equal to 11, then a particular alphabet will always go to a particular alphabet. Okay, that means this kind of schemes are known as monoalphabetic. For example, in case of substitution cipher also, if you are going to use this key, for example, A goes to D, B goes to F, C goes to H, so wherever in the cipher text you will get D, you know that if the this permutation is being used, then D must come from A. That means A will always go to D. So that means that the destination of A is fixed, the destination of B is also fixed. So this kind of schemes are known as monoalphabetic, and that is why this kind of statistical analysis could be used on those schemes. Why I have used statistical analysis? Because I know that the suppose some of the alphabets which are used mostly in our cipher text, I can assume that that cipher text may either come from E or maybe from T or maybe from A and etc. So this kind of statistical analysis is being done because the only reason is that whatever be the maximum occurrence of some alphabet, that comes from a particular alphabet. It if it happens that sometimes say A goes to D, sometimes A goes to N, sometimes A goes to G, If that could be the case, then you cannot use the frequency analysis. So people thought about that kind of idea that okay, uh, here in my two previous examples or three previous examples like SIP cipher or affine cipher or substitution cipher, each alphabet will go to a particular alphabet throughout. So if there could be a change that sometimes A will go to D, sometimes B will go to, say, A will again go to F, depending on the situation, then the scheme could be considered in a more secured way because you cannot have frequency analysis on that. So based on that, a scheme came up. This is known as Viginere Cipher. So this is an example of a polyalphabetic, not monoalphabetic. So just have a look at. Suppose my plain text is cryptology and my key is CIP. So this is my key. CIP is my key. Now let's try to see how I can use this CIP on cryptology. Okay. So as usual, we see cryptology. I can write it here, and if I put a roll number on that, so like A is 0, B is 1, C is 2, etc., then the value of C is 2. So I put it here 2. So value of R is 17 and so on. So this is my plain text. I convert it in terms of their roll numbers like 2 and so on. So this is my key. So I'll just repeat my key, CIP, again CIP, again CIP, and there are 10 many alphabets. So I use only C. And since 11, 12 are not there, so I am not in a position to use IP. Okay. So I just repeat CIP, 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 and this is the remainder. How many alphabets that you can use? You can use at most one alphabet here because only one alphabet is left. Okay. Similarly, if I put the corresponding values, C is 2, I is 8, and P is 15, and similarly 2, 8, 15, 2, 8, 15, and so on. Now I just make an addition modulo 26. So this is 4, this is 25. See, this is 39, and 39 modulo 26 is 13, and so on. Okay. So whatever I will get, I will put it back in terms of corresponding alphabet. So they are the roll numbers, I put it back. For example, here I have 4 and the roll number 4 is for the alphabet E and so on. Okay. So this is my cipher text. Now if you look at here in the word cryptology, O occurred twice. In case of monoalphabetic cryptosystem, O will go to a particular place. That means O will always go to some place and this O will also go to the same alphabet. But if you look at here, the keys are different. For this O, I have P. For this O, I have L. As a result, I get, for this O, I get D, and for this O, I get W. That means here O goes to different alphabets. That means this is not monoalphabetic, but this kind of cryptosystems are known as polyalphabetic cryptosystem. As a result, you cannot use the frequency analysis as what I have already mentioned in case of substitution cipher. You can use the statistical frequency analysis test for attacking this kind of schemes, but here you cannot attack by using the frequency analysis because one alphabet may change to another alphabet due to the use of different keys. Now you can see that it may happen that, for example, both the places you have the same key or same alphabet. For example, say here P, you might have here for this O, you might have also the P. In that case, they will go to the same alphabet, but there is a chance that same alphabet may take different values due to the use of different keys. Now the question is, how do you explain it using the group theoretic technique? Now you can understand that depending on the key. So here the number of keys are, the number of alphabets within the key is 3. So depending on that, we will divide the plain text. Say here, since the length of the key is 3, I divided the plain text in a part of 3 alphabets, and there might be some remaining. And based on that remainder, we'll use how many alphabets of the keys will be used. So here the plaintext, ciphertext and key space are nothing but Z26M, where M is the length of the key. Okay. Depending on that, so each of the plaintext M1, M2, Mk will be replaced by X1 plus, say X1 plus, X1, X2, Xm will be replaced by X1 plus K1. So K1 is the key, X2 plus K2 and so on, modulo 26. Similarly, the decryption would be considered as the value of y1 minus k1 and so on. So this is known as Viginere cipher. So you might have seen the movies. There are regarding this code. You know this movie which actually deals with the codes and all. So Leonardo da Vinci codes, Da Vinci Code. You might have seen this
Da
movie,
Vinci.
right? Da Vinci Code. So there you might have, who was the hero of that Da Vinci Code? Who was the
Robert
hero?
Langdon. Robert Langdon. Tom Hanks.
Tom Hanks. Yeah, Tom Hanks was the hero. And if you see that at the end, he was actually trying to get the message back from a kind of cylindrical instrument. So the idea was, so it was done by Da Vinci. The idea was Da Vinci wrote I mean, in his technique, Da Vinci wrote the plain text on a paper which dissolves in vinegar. So this is basically vinegar. Okay. So this Viginere cipher is, this is the name for vinegar. So Da Vinci wrote a plain text on a paper which actually dissolves in vinegar. Now he made an instrument in such a way that it looks like a cylindrical glass instrument kind of thing, and it has two layers. Inside layer, you have basically two concentric cylinders. Inside the inside cylinder, innermost cylinder, you put the plain text and then seal it. And in the outside layer of the cylinder, you put vinegar on it in such a way that the vinegar will not be able to go inside the inner tube or inner cylinder. Now he has associated with a kind of this kind of password in such a way that if you can rotate in a proper way the outer cylinder, if you rotate in a proper way, then you can detach the inside cylinder from the outside cylinder safely. Say if you put some, say SIP is the password, and if I rotate the outside cylinder into the place of a CIP, and then you can detach the outsider cylinder from the inside cylinder without any leak. That means the vinegar will not get into the inside cylinder. But if you try with any other password, for example, DIP, so this is the wrong password. And if you use DIP and try to detach the cylinders, then what will happen? The cylinder, the inner cylinder will be broken. As a result, the vinegar will get into the inside cylinder. As a result, the plain text will be dissolved into vinegar. So that was the idea. And as you understand that Tom Hanks being the hero, he just saw the rotator and he understood by some means, by some logical power he had. Usually the heroes, they do have. Uh, so by some chance, by something, he made this proper password and then he can detach the whole thing. And he got the plain text. So only heroes can do that, but for practical purposes, that won't be the case. But Leonardo da Vinci actually, he was a great person. So he was a multi-talented guy. You can see Google this Leonardo da Vinci, then you can understand he actually invented too many things. So he was an artist, he was a doctor, many things. Anatomy, he was a golden ratio concept, how golden ratio was attached with his name, everything. So you can have a Google, and he is a versatile guy. And he also invented this kind of crypto system. So that's a very interesting idea. But only heroes can break this. But yeah, so the idea was if somebody will try with a wrong password, and then that would be a kind of safety of the plain text. That if you try with a wrong password and try to open up the two cylinders, detached two cylinders, then the inner cylinder will be broken. As a result, the vinegar will get in and that will be dissolved. So that would be a protection. That means if your password, if your plain text fallen into a wrong hand, then also the plain text will be safe. So that was his idea. So now you can understand this is a generalization of again Caesarean cipher. Can anybody be able to say me how it's a generalization of Caesarean cipher? How can you think this as a generalization of Caesarean cipher?
So if the key is only one consists of only one coordinate,
Yes,
then it is a sequence.
exactly. So if the value of m is 1, then it is nothing but the Caesarean cipher. So again, you can understand that again this is a kind of extension of Caesarean cipher. So again, I'm giving you another very nice technique. It was done in 1929, and this is known as Hill cipher, and it is also polyalphabetic. That means same alphabet may go into different places. So here the idea is, suppose the plain text is this, and here the key is a matrix, n cross n matrices. So the entries are chosen from some ring or something, such that the determinant of this matrix is non-singular, non-zero. That means this is a non-singular matrix whose entries are taken from some ring maybe. So in this case, particular case, suppose the entities are from Z26. Okay. Now the idea is here this is your plain text. Okay. What this is your key, and if I multiply this, I will get again a vector of this kind, and this is my cipher text. Now you can understand very easily how to get back this. So both the sender and the receiver will have the same key, that means same matrix. So when the receiver will receive this, he will just give a inverse of this matrix. He multiply the inverse of this matrix with this to get the value of x1, x2, xk. So that was known as Hill cipher, and it's again a polyalphabetic scheme because x1 may go to some place y1 and same x1 may go to say some other y2 and somewhere else. Okay, so that is, this is also known as a polyalphabetic scheme. So here the size of the key space, you can understand that size of the key space is the number of non-singular matrices from any ring, maybe from Z26 or something. It may, you may change it to some other field also. You can change it to other ring also depending on your scheme. But in this particular case, it's only 26 alphabets. That's why I have taken Z26. So the size of the key space is nothing but number of non-singular matrices whose entries are from say 26, and then you can calculate how many are there. So let us have a look. Suppose the key is this, and suppose the password is, suppose the plain text is love. Okay, so you just, depending on the number of rows or columns, you just divide it into LOV. So LO corresponds to 12 and 15, then multiplied it by this matrix modulo 26, you get this value. So this is your cipher text for LO. Similarly, this is your VE corresponding to that, you just multiplied it by the same matrix, and whatever you get, this is your cipher text. So JG is a cipher text corresponding to LO, and HM is the cipher text corresponding to VE. So this is your basically the cipher text. You send the cipher text to the receiver. So when the receiver will receive this, he already had this because they are all examples of symmetric cryptography. That means both the sender and the receiver, they are going to use the same key. So whenever they will get this, they will receive this as a message, and already they had this as the key. Then what they will do? They will simply make the inverse of this and multiply it. Whatever they will get LO and V back. So this is known as Hill cipher, and that was quite old. Using computers, you can do this because now you can find all the so that is the search space is the nothing but the number of all non-singular n cross n matrices over the ring Z26 plus dot. So that's what. So that is known as Hill cipher. Now let me have a, can you see this screen? Is it visible to all of you? So please take a screenshot of this and try to solve this problem. Yeah, so this is an exercise. So try to solve this problem. So let me read this problem. A rich mathematician was murdered. So a rich mathematician was murdered, and Sherlock Holmes, along with John H. Watson, who was his assistant, found a three-digit 666 engraved on the wooden floor by him. So both of them, they were so British, so that's why they had wooden floor, not our cement floor. Most of the cases, because it was during that time it was like the cold, due to the cold weather, most of their houses are of wooden floor. So both Sherlock Holmes and his in the murder scene, they went, they found that on the floor just beside the dead body of that rich mathematician, 666 is written on the floor. Since it was a wooden floor, that's why by some means he has engraved it. Okay, so they have seen 666 by him. I mean the mathematician by his nail. Okay, by his nail he just engraved 666. Sherlock deduced that the digits might refer to the password to the secret safe which contains all his wealth. That means some of the say locker or something, which could be the 666 could be the password for that locker. So first initial phase, the investigator officials or Sherlock Holmes, they thought that 666 could be the password for the locker. Soon enough, they found that the safe, but soon enough they found the safe. That means they found the locker, but 666 was not the password. That means they found the locker, but they found that 666 is not the password of that locker. That means 666 should have some different meaning. After soon more investigation, they found the matrix this. Suppose they found this matrix written on a paper in his secret drawer along with the following meaningless sentence written in English on a piece of paper. So they got a kind of cipher text. This matrix 666 along with this meaningless cipher text. They understood immediately, sorry, they understood immediately the meaningless sentence may lead to a clue to open the safe or the locker. They tried to guess the sentence but unable to do so. Certainly, being a good friend of Sherlock, your name came into the mind of Sherlock Holmes. So, your individual name will certainly be clicked in the mind of Sherlock Holmes. He came to you immediately and asked for your help. Sherlock Holmes asked you to decode the message. Being an intelligent mathematician, you guessed the meaningless sentence may be obtained using Caesar cipher. Now, could you help Sherlock Holmes to get the password of the safe? So, whatever hints that I am giving you, say I have already, suppose you being a very intelligent mathematician, you just having look at it and you could understand that this could be a ciphertext obtained using Caesarean cipher. And since in your syllabus or I have all I mean I have only dealt with this matrices in case of Hill cipher, so you understood that okay, this may be something linked with your Hill cipher. Now with that all the hints and you being an intelligent mathematician, can you decode what could be the password of the safe? Please take a screenshot of this slide so that you can try it and let me know in my next class. Okay, so please don't take much time now. I will go to my next slide, but this is a kind of homework that you can think of, and you can answer the password in my next class. So please take a screenshot of this thing. Okay. So as I mentioned, there are plenty of attacks in the history of World War One. There was another machine which was known as Enigma machine. So this Enigma machine was actually made by the Germans, and the Germans were very proud of that machine. So they thought that nobody could break this Enigma machine. So it was a kind of machine through which they encrypt their message and they send the message to some other guy, say some German people who are in the battlefield. And since they also have the Enigma machine, they could only decrypt this and nobody else. So they thought that in the world nobody could break this machine. But unfortunately, it was not the case. And in 1932, Martin Janeski, so he was a Polish mathematician, very young at that age, only 27 years old. He was a mathematician, but he was doing with the British intelligence and all. So he finally broke it. How it was broken? Like during this war, sometimes the Germany they lose some field, and suppose I am one of the German soldiers who are carrying say Enigma machine, and suppose by chance I lost the war at that battlefield. So my Enigma machine will be captured by the enemies, say British. So physically, the British were able to gather few of the Enigma machines. Then they have sent it to the British intelligence, and somehow this machine actually reached to Martin Rajewski. Okay. So Rajewski, after opening the machine and after doing lot of mathematics, he could understand the what is the basic mathematical things that are happening. So there was some mistakes were there in Enigma machine, and he actually pointed out that mistakes, and he finally decode it. He could able to decode it. That means if somebody will send some message using Enigma machine, he got an algorithm how to decode it. But the British intelligence did not, or the British side did not reveal the fact that they have already encoded or they have already broken the Enigma machine. Now Germans were very much proud of their machines, so they were keep on sending all the important informations uh, in the battlefield, and the British they actually intercepted all the machines, and since they had the algorithm to break it, they decoded all the informations, but they did not reveal it. So what happened when Germany say, suppose Germany send a message to some of his warfront that okay, attack to this city. When they started doing the attacking, beforehand the British soldiers they captured that place and they were hidden, or they took the position of the proper places of that particular city, so that when the German soldiers get into that city they are trapped. So after few such incidents, the German soldiers or Hitler, they actually came to know that something happened, and it was too late. And by that time, Germans they lost many of the wars. And in the First World War, it is considered to be one of the reasons why the First World War actually ended little earlier because of the this attack on the Enigma machine. So this kind of scenarios are very important for war viewpoint, where if some of the machines are being broken, then the complete attacking system of the soldiers could be destroyed. As a result, you may get some extra advantages. Okay. So now I will come to another very important topic of cryptography known as public key cryptography. So here, if you go back to our earlier scenario, there where the sender and the receivers are there. But the problem is, suppose the senders wants to send some message to the receiver, but the problem is both of them they stay far apart, say opposite half of the world. So if this boy wants to send some message using internet, then this bad guy will always try to listen what is being sent. And not only that, this bad guy may modify the original message, and when this guy will receive that modified message, she may think that that message might have come from this boy. So some miscommunication or misconception may happen. As a result, there must be some misunderstanding situation may occur. So as a result, this boy will certainly do some encryption and send the encrypted message. Till now, whatever I have given you the examples, the point was both of them, both sender and the receiver, they will have the same key. See, if you look at this case of Julius Caesar, it was k equal to 11. In case of Affine Cipher, it was an ordered pair. In case of, say, Hill Cipher, it was a matrix. In case of a Substitution Cipher, it was a permutation. So both the boy and the girl, they should know the same key. Now, if they are staying far apart, it may also happen that this girl may not know this boy, but still this boy wants to send some message to this girl. Then what will happen? So how they are going to communicate with each other to have a common key? So unless they will have a common key, they cannot send a secure message. Because if they want to share the common key, suppose he wants to share a common key, he may send the key using, say, Gmail. Then what will happen? The Google company will be able to get the message of about the key. So the Google will able to understand what is being sent as a key. So he cannot send the common key using some insecure channel. And it was thought that nobody could do this. And even till 1976, it was assumed that it is impossible to have two different keys at the two different places if they are far apart. But in 1976, Diffie and Hellman, I will give you talks on the paper separately, but not today. Diffie and Hellman, they came up with a concept that is known as key exchange protocol. So Diffie-Hellman key exchange protocol, where they have shown by means of some technique of mathematics that okay, even if they will have some insecure channel in between, after communicating with each other using some uh, insecure channel, at the end they will finally fix up a secure key after some of the communications through insecure channel. So I will come to it later on, but for today's scenario I will give you a concrete example where both the boy and the girl, they will be able to communicate with each other uh, having two different keys, not the same key. Okay, and they don't require any prior communication with each other to have a secure communication. So that is the basic idea. But before going to that, let us have a look at our normal scenario, which I can explain using some examples. There is one university, and as you know that there are controller of examinations, and usually we do have also external paper setters. So who are external paper setter? That means the paper setters who are not from that university, who are not the faculty members of that particular university. Suppose we have a examination system, and he is the controller of examination, and he is the external paper setter. So why external paper setters are required? So sometimes in case of exams, we appoint some of the external paper setter, and there, after submitting his paper, there will be another question paper from internal faculty members, and then there would be a kind of moderator. So this moderator will basically take some questions from the external paper setter as well as some questions from the internal paper setter, as well as he has a liberty to put his own questions inside this, so that a complete set of question paper can be made. So that is the idea. So the idea is, suppose controller of examination wants to happen the exam in a very transparent way, so he appointed some external paper setter, And as the external paper setter is not a faculty member of that university, so usually he stays little far off. So the best thing is that he prepares a question paper and he sends this question paper to the controller of examination personally. That means he makes the question paper and he puts it into an envelope and gives the sealed envelope to the controller of examination personally. But most of the cases that is not the case, because as he is not a faculty member of that university and he stays maybe far apart, so most of the cases uh, both the controller of examination as well as the examiner will have to rely upon a third party, usually the postman, through which this paper setter will give the question paper to that controller of examination. So that is the usual process, that a postman may take the question paper from the question setter and then it gives it to back to the controller of examination. But this controller of examination, being a person from a world of cryptography, he wants this to be done in a very secure fashion. Okay. Now, can you give any suggestion that how this question paper or this paper setter can send the question paper so that this paper setter won't be able to find the question paper? So it should be a kind of secure way. How? Any guess that you might have?
Sir,
Yes.
if the controller of examination seals the envelope that no one can break, so he sends it. Then the external paper setter receives it, so he cannot open the seal. So what he does, he applies another seal. Then he sends it again to the controller of examination. So the controller of examination removes his seal, and then he resends again. So now the external paper setter has the envelope with the seal which he himself applied, so he can open it now.
So what do you mean by a seal?
Seal might be a lock or.
Okay. Yes. That is a good idea. So I will basically doing the same thing here. Any other suggestion? Any other suggestion? Okay. So I'm going to give you an innovative idea. So that is actually related to the idea of public key crypto system. That's why I am doing it in an that complex way, but it's very innovative. So as I mentioned, this controller of examination, he is very particular about security. So what he does, he made a kind of lock, key and box for a paper setter, and he being very particular, he ensures that no copies of this lock and keys are available in his office. That means this is a single lock and key, no copy is available. Okay, and this is a box. What it does this, he sends it this box as well as this lock and key using, so somebody is trying to join the mission. Okay, so somebody wants to not somebody okay, so he sends this lock and key and the box using this postman to this external of examination. Now this external examination examiner will receive this box, lock and key, and he prepares the question papers, and when he finds time he puts it inside the box. Now he makes a lock and key. Now if I ask you the question how he sends this lock and key to this controller of examination by using this postman, any suggestion?
So he can use two postmen. One carries the lock and the other one is key to
Very
send
good.
the controller to.
Very good. So I will come to that topic after few, maybe one class on that. That is known as secret sharing. That means he may use two of the postman one will carry this locked box, because he cannot give the both lock and key and the box to this postman, because if he gives it and if he has some problem, then he will suddenly open that lock and key and able to see the question paper. So what he will
Or
do? Yeah.
sir, sir, what
Yes.
other what he can do is that actually it's the same thing almost, but he can first send the locked question paper while keeping the key to himself to the controller examination, and when the controller says that he has received uh, the parcel, then he will send the key.
Yes, almost the same thing as secret
Yeah.
sharing, as I mentioned. I mean, this kind of concept you might have seen in case of, not now, but I mean, few days back also, or few years back also, you might have seen that whenever you have the credit card or debit card, the card first comes to you by post, and then the key or the pin comes after a few days, again using the post. It's not like the pin and the credit card physically they reach you. So it's basically kind of secret sharing. First the card comes to you, and then after a few days, again by post, maybe with the same postman, the pin comes to you. So that's the similar concept here also. So that is also known as secret sharing. I will come to you, I will talk on that maybe on a different day. So this is one of the ideas, that he can send it by using two different channels, or maybe two times after say sending this, or then he will send the key afterwards. So that is one concept, but I am going to give you another very innovative idea how to do that. Okay, the idea is he will send it to the postman, and then the postman will send it to him. Now, since this is the only key and nobody has any copy of this key, even the controller of examination won't be able to open it. What he will do? He will put another lock and key here and keep the key with him and put a lock on the same box, and he will send it to the external of examination. Now the external examination has his own lock and key, so he can open it and he can send it to him. Okay. Now,
Sir, I did not understand.
okay. So up to which you understood? This part you
Yes,
understand?
yes.
Okay.
Like, yeah,
Yeah.
yeah.
After
After it
that,
goes to the control examination, after that,
controller of examination will bring another lock and key. Okay. And put the lock into the box and keep the key with him, and sends both the lock along with the box to the external examination. Okay.
oh, okay, okay, okay. Yes, sir, yes, sir.
Now
Okay.
the
Hmm.
external has his own lock and key, so he can open this and sends the locked box to the controller of examination. Now the controller of examination has his own key, so he can open this and he gets the question paper, and he is very happy now because it's done in a very secure fashion. So is the protocol clear to all of you?
Yes, sir.
Anybody who is not yet comfortable with the scheme, is it clear to all of you? Okay. So it's a very innovative way of sharing things, and that is the basic idea for public key crypto system. But as I mentioned, that cryptography is not goes in a straight line. So this postman might be a bad guy and even more intelligent than the controller or the external examiner. So what he does? So if I again repeat the same process, like controller gave the lock key and the box to the external to the postman to send it to the external exam paper setter, what he does? He brings another lock and key and put the same box and gives it to the external paper setter. Now there is no clue to the external paper setter that this box and lock and key. So this lock and key has been replaced. So what he does, he puts the question paper inside the box and make a lock and keeps the key with him as the protocol says. So he sends it to him. Okay. Now what the postman will do, the postman will put the lock given by the external controller of examination and he will again send it to him. Now the external paper setter will understand that okay, it comes from the controller of examination, so he will just reopen it and gives it to him. Yeah, gives it to him. Now what will happen? This bad postman has both lock and key, so he will open it. So, sorry, he will open it and he will see the question paper. He solved this question paper. Whatever he wants, he can do this. He can modify the question paper. He can completely change the question paper and again lock it and sends it back to the controller of examination. Now the controller of examination will think that it comes from the external paper setter. He is very happy. He will put the lock and key to that box and keep the key with him and sends it to him. Now he has already seen the question paper. He has the lock with him, so he'll just open it and again sends it to it. Now he will now think that okay, it's the final round of the protocol and he will open it and he will get the question paper. Maybe the question paper might have completely changed or the bad guy has already seen the question paper, so he will receive a question paper which is already modified. So that could be a situation. So is the attack clear to all of you, or shall I repeat? Is the attack clear to all of you?
Yes, sir. Yes, sir.
Anybody?
So can you repeat once more the attack part?
Okay. Okay. So as usual, the controller of examination has his own box, lock and key. Now he sends the lock and key to this postman, but the postman in between produces a similar looking lock and key. And he keeps this lock and key given by the controller of examination and changes it to these three pair. That means he gives his own lock and key along with the box and sends it to the external paper setter. Now this external paper setter will find that okay, it might have come from the controller of examination. So after completing his question paper, he will put inside the box and make a lock of it and sends it back to the postman. Now what the postman will do? Postman will now put the lock given by the controller of examination and keeps the key with him and sends it back to the external paper setter. Now what the external paper setter will understand? The external paper setter will understand that it has come from the controller of examination. So he is going to open this lock and key and gives it back to the postman. Now postman has the key for this lock. So he opens it and opens up the question paper. He modify the question paper. He may modify the question paper, or he may replace the question paper, or he can solve this question paper. He might have the proofreading of the question paper. Whatever he likes, he can do. And after doing that, he will again put the modified question paper inside the box and make a lock using that and sends it back to the controller of examination. Now the controller of examination will think that it has come from external paper setter. So he will be very glad to put his lock and key to that box and sends it back to the postman. Now the postman has his lock and key, so he can open this and sends it back to the controller of examination. Now the controller of examination will understand that it has come from external paper setter. So he opens up his own lock and key and gets the modified question paper. So he will be very happy with the modified question paper. So that's the attack. Is that clear to you?
So the main concept behind this attack depends on the part that the mailman is able to decrypt the message of the controller of examination,
No. I
or has
mean,
the key to it.
he has the key. I mean, he has actually whatever he did is. I mean, if you want to think in terms of this encrypted scheme, so it's not yet any encryption, right? It's just a simple protocol. It's not related to any encryption scheme yet. But after giving you the idea of public key crypto system, you will able to understand how this is being done. So you might have seen the Mission Impossible, one of the series, Mission Impossible series here, which was in the desert. So there you might have seen that it's known as man in middle attack. That means somebody is actually trying to convince you that he is the guy, but in between he is doing the job. Like he is taking from someone else and sending to someone else. So those who have seen this scene might now able to associate the idea behind this. So not yet I have done any kind of encryption concept, but this is basically the encryption concept is actually related to this kind of idea. Okay, so this encryption or this attack is known as man in middle attack. So now you can understand that some of the extra uh, protection that one should take to make it more clearer, right? But when we started with the scheme, nobody could even imagine that the postman might be of that kind, and he may fraud or he may be able to attack the scheme, the protocol was very simple. And at the very beginning we also didn't thought about this kind of attacks and all, and that's cryptography. Because when the simple credit card started, then nobody thought that some fraud could happen, and then suddenly they found that there are plenty of ways to fraud it, and then day by day this is becoming more and more complex. The same thing happens with the operating system. So if you go to, say, if you have Windows 98, that's very simple, very light, but now you can see this Windows are very complex, and it's huge. So the size of if you install a Windows 10, this size is huge. I mean, the previous version of your laptop may not work because it's a huge size operating system. Why the size is huge? Yes, it has introduced lots of extra features, but at the same time, it's also providing a lot of security. That's why very frequently, maybe say after 2 months or 3 months, you might have seen that your original Microsoft Office or your original Microsoft operating system, they are being updated. Even for Linux also, the same thing is updated because people are trying to find many loopholes. And wherever you find some loopholes, many scientists are there who are trying to resolve that problem and make it more secure. Again, they patch it, they provide a patch like a new updated version of your update. If you update this, then the that part is secure. But again, after a few days, many people will find some new threat on it, and then again a new version should be installed or upgraded. Otherwise, there might be a threat that somebody can get into your machine and do some kind of harmful things. So that is the idea of cryptography. That's why it's very dynamic, very fast. Many scientists are working on it, and it's really a hot topic in today's scenario. Okay, so again, I will come to another the idea now how it can be explained mathematically using in terms of cryptographic viewpoint. So here, as I mentioned, it's a sender and the receiver, and both of them, they are staying far apart. As a result, they cannot share the common key securely. So they should have something else different. Okay. So if I ask you a question like, suppose this boy wants to send some message, say by using say WhatsApp to this girl, then who should take the initiative first? Whether the boy should take the initiative first or the girl should take the initiative first, so that a message from this boy can be reached to this girl. So if I ask you the question, who should take the initiative first? Is the boy or
Obviously, the boy.
the boy? So if you think it very quickly, then you must answer that the boy should take the initiative first. But if you think little deeply, that if the boy wants to send some message to the girl using WhatsApp, then it should be the girl's duty to have the infrastructure first. Suppose the girl does not have any mobile, then will the boy be able to send the message using WhatsApp? So even if the girl has mobile, she has not installed say WhatsApp, then also the boy won't be able to send the WhatsApp message to the girl. That means the infrastructure should be made by the girl first. That means if the boy wants to send the message to the recipient, it's the recipient duty to first have an infrastructure so that the boy, if he wants to send, will able to send the message. That's why it's the girl's duty to have should have a working mobile with a proper connection, and also the WhatsApp is installed within her mobile. Then it's the duty for the boy to know the mobile number of that girl. So unless the girl will have the infrastructure, the boy won't be able to receive the information about the mobile number. So after the infrastructure is ready, the boy will somehow will able to know the mobile number of the girl, and then using that mobile number and the WhatsApp number, he will be able to send the message, and then the message will receive by her. In public key crypto system, the similar concept is there. If the boy wants to send some message to the girl, then it's the duty for the girl to have the infrastructure. For example, suppose somebody wants to send me the email. So the first thing that I should have an email ID. Now, when I create my email ID, I have two components. One component is the email ID. For example, abhishek.maths at the rate presidencyunip.ac.in. So that is the email ID. Another part is the password of that email ID. So I have two components. One component I make it public. That means in my website, or if somebody will ask me that what is your email ID, I will certainly share my email ID, but I will certainly keep the password of that email ID with me secret. That means I have two components. One is my email ID that I can make it public, and there is another component, that my password. So if somebody will send me to me some email, then only me can decrypt it, because I have the password to get into my mobile to my email account, and from my email account I can get the email ID, yeah, the message that was sent to me. That's why if somebody will send from my email ID to somebody, and if that is controversial, then the first thing will happen that police will arrest first me, or some inquiry will happen against me, because it's not feasible, or it is not supposed that my password, my email's password is known to others. So then there are many techniques to know that from which IP it has really been sent, and then what was my coordinator, etc. But initial phase, at a very first glance, the problem will happen with me, because somebody might have sent on my behalf some email, some controversial email to somebody else. But later on, when the investigation will go on, then it may reveal that okay, I am innocent, because somebody might come to know my email ID, or somebody might have hacked my email ID, and he gets this email ID and then password of my email ID, and then he sends on my behalf. But at the initial phase, it's my responsibility that nobody should know the password of my email ID. So what is I'm trying to say is that here, when the girl is going to make the infrastructure, the girl has two things. One is public, that means like my email ID, Another thing is the private, that is the password of my email ID. So in public key crypto system, we call it two keys. One is public key that is known to all, another is private key that is only known to this girl. Now she will make the public key public. That means everybody will know the public key. So in particular, if the boy wants to send some message to the girl, the public ID or the public key is also known to this girl boy, because somehow he will able to collect the public key. Based on that public key, the boy will send the message to this girl. Now, based on, since this public key and private key or secret key are related, so since the boy has made or encrypted the message using the public key and only the girl knows the private key, only the girl will able to decrypt the message and nobody else. Since this boy, this bad guy does not have the access of this secret key, he will not be able to get back the message. So that is the basic idea, naively speaking, that is the basic idea of public key crypto system. So is the idea clear to all of you? Any question? Okay. So let us give some example. So it was actually came up a little late. So in 1976, this idea came, but Diffie and Hellman failed to provide any of such schemes. So they gave an idea how to have the common key, but they gave the idea of public key, but they failed to give any of the concrete scheme. But the first concrete scheme came in 1978 by three scientists known as RSA Public Key Crypto System. It was made by Rivesh, Shamir, and Edelman. So please have a look at the chapter 12 or any internet or any cryptography book. So RSA crypto system will also always be there. So this is very important, and still now we use RSA crypto system while you do some online banking and all. Okay. So what is the idea for this RSA public key crypto system? Let me try to explain. Okay. So suppose it based on a computational problem, and for mathematician it's really difficult to believe that it's really a hard problem. So what is that problem? If I ask you, if I give you 35 and if I ask you, can you factor into prime factors this 35, you will readily say that okay, it's 5 and 7. If I ask you, can you factor this, you will say that okay, it may take some little more time, and you will able to say that okay, it's a product of these two primes. If I give you this, you say that okay, I'm not going to do it by hand, but suddenly a small program will give me this factorization, and this is the product of these two primes. Okay. So the idea is factorization. That means if I give you some number, you need to give me the prime factors of that number, or in a prime factorization way, you need to return me back. But if I give you this number and ask you, can you factor this into prime numbers? So you'll be stuck, because your programming will not help you in giving you these values, because your program may not run with these big primes. You will be happy to know that not only you, but a supercomputer will also not be able to provide you the factorization of this big number very quickly. So it may take say 100 years to give you the factors, because this is the product of these two big primes. So first of all, I have already given you an example of 904 digit long primes, but here it's around 300 digit long primes. So each of P and Q are around of 300 digit long. So this number is nothing but the product of these two big primes. So first question that comes to our mind is, are they really primes? If they are primes, how did I get these two primes? And you'll be surprised to know that our this laptop are capable of finding this big primes, and very easily. And in your course, though we do not have this primality testing in details, but I will show you, will give you a very brief, but without any proof, just an algorithm, how to get this big primes. Okay, so in our course we have quadratic reciprocity, and as an application of quadratic reciprocity, I will show you how to get this big primes. Even our small computer, maybe say I will show you how to get this big primes. So for example, for this, maybe if I write only this code, say next prime, say 23. So it's after 23 we have 29. So you may think that okay, it's very small number. Now have some, what is the next prime of 2 to the power 100? If I put it, it will give me answer very readily. If you are saying that okay, 2 to the power 100 could be a small number, why not 2 to the power 1000? So it will take little more time. You can understand it will contain around 300 digits. So this is nothing but the next prime. So this slash means next line. So it's a whole continuation, and this is the prime that I mentioned. You can see that 9673. So this, okay, it could be any other number maybe. So it was the prime. Okay, so they are, I think, different primes, but they are almost of this size. So this prime is almost of this size of this. The number of digits are almost the same. So how this small code is giving me this big prime? So this is basically the prime that I explained here. So this is the next prime of 2 to the power 3000. Now you can see that it took maybe 2 to 3 minutes to give me this prime, this big prime. So it's very easy to get this big primes, and I will show you how to get this big primes using some algorithm which are probabilistic primality testing algorithm. But the point is, even if we have an instrument, or even if we have an efficient algorithm to get two very big primes, you can make the product of these two primes also very easily. But if you make the product of these two primes and get this n, from this n is difficult to go back to p and q. That means one way is easy. That means if you have p and q, you can make a product to get n very easily. But if you have n, then from n it's really difficult to get back pq very quickly. Mind that I am talking about finding the primes using computers, that means hardware. Till now, there is no efficient algorithm known by using the hardware or the computers to get the primes from n very quickly. That means there is no known algorithms are till now known to people or known in the literature of cryptography or number theory, which can provide you from n to pq. But in case of quantum computation, there are algorithms available which are efficient, which can give you the factor of this n very easily. But unfortunately, till now, the quantum machines are not available. It's like I say in that way, it's the Ramayana is ready without the introduction of Ram. So Ram is not here. Ram here is the quantum machine, but the algorithm is ready. So if one day, if somebody or some scientist are will able to provide the quantum computer machine, then suddenly using that machine one can very easily factor this big n. But unfortunately till now not such not such quantum machines are available which are capable of factoring this. So Google has already claimed that they have made something, but IBM, they oppose their claims, and now it's a kind of tussle between IBM and Microsoft, not Microsoft, Google, that IBM is claiming that whatever claim that Google made is not appropriate. On the other hand, Pichai, Sundar Pichai is claiming that they have made something which the traditional computer might have taken 1,000 years, but they solved it very quickly. So it's now still in a tassel moment that nobody is agreeing the other's argument, but nobody knows. In near future, maybe this quantum computers will come, and lots of research and lots of fundings are there for this quantum computers or quantum cryptography. People are still working on it very hardly to find the quantum computers or quantum computing, but till now nobody could find a very efficient machine that can handle to break this big primes. But as I mentioned, the algorithms are there, so if one day the quantum machines are available to handle these big primes, then this n could be factored very efficiently, very quickly into these primes. But till now, our normal supercomputers, I mean, supercomputers now you can think that it's very powerful computers. For supercomputers also, this is not very easy to find an algorithm to break this n to PQ. So based on that idea, the RSA crypto system was there. So I am stopping it here. Now it's your time. For the next class, you read RSA crypto system, and I will show you few more applications how RSA crypto system are useful